Hi, everybody. This is the walkthrough video for Tuesday. It is whatever day it is, February 24th in try 3 week 2. I just got off Zoom and my brain is much slower than it typically is. So, all right, for those of you playing along at home, here's question 21. It says, in a hypothetical population of beetles, there's a wide variety of color matching the range of coloration of the tree trunks on which the beetles hide from predators. The graphs below illustrate 4 possible changes to the beetle population as a result of a change in the environment due to pollution that darkened the tree trunks. So you can see along the x-axis is beetle color, along the y-axis is population frequency. The dotted line is the original population, and the solid line is population after pollution. So here's the question, and I'm going to have you zoom into the video for a moment, but I did want to show you the first thing I do when I look at one of these questions, if it says which of the following indicates the most likely change in the coloration and a correct rationale, I'm going to look and see if each of these is set up to match one of those. So indeed, A is about 1, B is about 2, C is about 3, and D is about 4. Now, for this one, you should read through the text just to hear that rationale in your head. But honestly, if you could have just answered it based on what happens after pollution, what's the rationale for that, you should go ahead and do it. So if you're playing along at home, which answer A, B, C, or D is correct, and then a sentence or two about why you know. All right, no storytelling today. Instead, a really charismatic animal known as the pocket mouse or the rock pocket mouse. Today, we're going to think about whether populations are undergoing genetic change and how we know. This means we're going to finish the Hardy-Weinberg Pogel because you're going to look at some real data about real animals, the rock pocket mouse, tomorrow as part of your classwork. Now, mutations are the reason that we have different alleles, right? And then when environments also change, this thing about populations undergoing genetic change can definitely happen as a result. So here are guiding questions. Again, we told the story of the frigifers last time. You should head to the slides. Remember, they're linked for each day. Oh, they're not yet. I'll make sure those are uploaded. My apologies. And you're going to watch this really cute 10-minute video about the Snickers bar of the desert. There's only one animal getting eaten. It's by an owl really early on. It's only for a moment. The story in here is really beautiful, and you're going to see it quite a bit over, like, they love to write questions about the Snickers bar of the desert. But as you'll see when you come back, there really is this distinctive advantage to being a mouse with dark colored fur on the dark lava flows, and for a light colored mouse to be on the sand. And we'll think about more about that tomorrow. Just a note that we are talking about a lot of stuff. Some of this you've seen this year, some of this you haven't, but like these stories about change and also universality are kind of at the heart of Unit 7. So whether we're thinking about the story of the frigifers, or I don't know if you know this, but the beak sizes, the Grants who worked at Princeton actually measured during droughts, and it turns out that the beaks change, probably so that because you can crack harder seeds that way. But there are also things that are like absolutely universal, right? Like glycolysis, membrane structure and function, cell parts, and even the like code of life and how that ends up happening. So this idea about population change is equally undergirded by this idea of common ancestry through all these things that are common in life. So today, we're going to talk about the gene pool. I drew it as a pool because I think I'm funny. And it doesn't have to do in the Pogel with how many light color or dark colored beetles there are. It's just a way to think about what the proportions are at large of those dominant and recessive alleles. And for Hardy-Weinberg, we are never, ever going to ask you about more complicated phenotypes, just so you know. I've never seen a question like that. So remember, we're thinking about P as the percentage of dominant alleles, big B in this case, and Q as the percentage of lowercase alleles or recessive alleles in this gene pool. And of course, you remember from being younger that no, hopefully you remember that the only thing in here are those two things that's going to equal up to 100%. And we're going to switch from thinking about percentages to thinking about decimals between 0 and 1 as we think about taking that same idea and squaring it. Remember FOIL? If you do that, you end up with this equation, which, as you learned from the 7.5 notes, is the second Hardy-Weinberg equation. And then when we take this idea, P and Q, and you physically square it, that means you get something that looks a little like a probability map for a Punnett square, but it's not a Punnett square, which we'll come back to in Unit 5. Those buddies are divided into four equal sections because either you know the gametes of the ancestors, the direct ancestors, or you're making a guess about them in those problems. But as different people showed in different periods in our class, you can't do that for populations. So, like, if Big B is actually very, very rare, there'll be an even smaller filled in square there, and a lot more of that map is going to be that homozygous recessive, the population, that percentage of the population. So, one more time, P and Q tell you about the percentages of different alleles in the gene pool. P squared, 2PQ, and Q squared tell you about genotypes and phenotypes. So you get a little practice today, you get a little more in time to come. So your cool down for today is to write down expressions for each of the following. You can just rewind the video after you've written things down and take care of it. All right. I hope you're doing well out there. We will see you soon. Take care. There we go. I'm going to stop.